Okay, so we will continue with what we call closed loop testing. Okay, closed loop testing. That is mostly a manual method. Okay, and actually we will in the follow-up lectures we will see open loop testing. But open loop testing cannot be always done, okay? Which is more intuitive. We apply a step input to the plant and we actually record the response of the plant and we fit a certain model to the response, okay? But in the cases where we have basically an open loop unstable plant, okay, if the open loop plant is unstable, I mean, one might argue that you can still try to fit a model, but basically using an open loop unstable plant, applying a step input to it is often impractical because you make the system unstable, you can break something, the system may completely fail. In simulation, obviously, you might find a way of fitting an open loop unstable model to an open loop unstable plant, but in practice with the physical system, that's not feasible. Also, if the open loop system is underdamped, open loop system is underdamped, that means it has oscillations, it becomes more difficult to actually manually fit a model, okay? So in these two cases, for an open loop unstable plant and for a system that is underdamped, we will actually we will resort to closed loop testing. Okay, so this is known as a closed loop tuning of the PID controller. Obviously, this can also be done with a computer with an arbitrary, in an optimization manner, as we have discussed before. But the question here is, can this be done? Can this be done manually? Okay, and the answer to that is yes, to some extent, using the Ziegler-Nichols method. Okay, so we will discuss that right now. Is the concept clear? So let's describe the method. The idea behind the method is basically to find the boundary of stability and back off from that boundary by a safe amount to obtain a reasonable response. Okay? You know that the boundary of stability is where the closed loop poles are on the j omega axis. Okay? So idea is to find the boundary of stability, and back off to a safe set of parameters. But in fact, apart from this idea of finding the boundary of stability, the rest are based on experimentally derived formulas, so they do not have a theoretical basis in a sense. But I will later put up a video example for you that actually applies the method when all the models are available, and you see how or what kind of a model, what kind of a controller this method gives you. Okay, so the method is composed of step one. You basically shut off integral and derivative control. Okay, shut off integral and derivative control. Obviously, if you are working with a ready commercial controller, you can do this by either really turning off those modes of control, or you can play around with the coefficients to make these two terms vanish in the final controller formula. Okay, or let's for example tau I be going to infinity and tau d go to 0. Okay, to eliminate the corresponding terms from u of t expression. Okay, so you then turn closed loop control. In this case, P control is remaining on. What does that mean? That means you put the system within a feedback loop where inside you have the controller, but it's the P controller right now. And you activate the control loop and you run the system like that. Okay? Sometimes in automatic, in commercial controllers, you have automatic mode versus manual mode. This means you put the system in automatic mode, okay, versus manual mode. Manual mode is when you apply something to the system directly. Okay. Now you have only P control and you want to test the stability limit of the system. So what do? You start increasing the gain, the proportional gain, until the system is actually at the boundary of stability. Okay. How do you identify the boundary of stability? Well, the system will start having oscillations. Okay. And the oscillations will grow, and when you're on the j omega axis with your poles, the system will have sustained oscillations. Okay, and that is why the method is named as continuous oscillations method. Okay, so adjust Kc such that you get undamped response. Okay, so what it looks like, well, if this is your step response, okay, and this is your reference, right? So what you will get is that instead of having basically a damped response like this, and instead of having an unstable system, you will basically get, sustained oscillations. Okay. So if you have, if you observe an underdamped response, okay, so sorry. If you have an underdamped response, sorry, you increase the gain, to approach the j omega axis further. And if you observe a mildly unstable system, you decrease the gain. Okay? So obviously this is logical for systems that basically have dominant second order poles. It can be a higher order system, but there will be a dominant response. Okay, so as you increase Kc, okay, increasing Kc, you will basically move on towards the j omega axis. So when you hit the j omega axis, you will observe oscillations that are not decaying with time. Okay? So once you do that, you record certain parameters of that response. Okay? So obtain Kc. That is given a special name in this case. It's called ultimate gain, KCU. Okay? And you also obtain the resulting frequency of oscillations. So you obtain the period actually, and that gives you what is called the ultimate period. PU. Okay. So from this undamped response, you obtain two parameters, the ultimate gain and the ultimate period. Okay. And that would give us a particular design. So the design parameters, that would give us that will actually give us what is called the 0.25 decay ratio. Also known as DR. And let me illustrate what that means. That is a response where the oscillations are decaying with a certain rate. Let's say this is our reference signal. So so the response will basically have an overshoot and then a second overshoot and so on. So if you call this overshoot A and you call this overshoot B, decay ratio is actually the ratio of B to A, and that is for this design 0.25. So you have 1/4 of the initial overshoot at your second overshoot. Okay. So that's going to give us a design for Kc, tau I, and tau D, and will actually give us all three kinds of controllers except the PD controller.
Hocam bir şey sorabilir miyim burada?
Yes, go ahead.
Şey dedik ya, şimdi A ve B oranı işte 0.25 oluyor. Burada yani oscillation'a decay ediyor. Peki bizim burada seçtiğimiz KC şey değil, tam sustain, yani tam j omega aksisindeki KC'yi seçmedik mi? Ultimate KC olarak.
Yes, but I haven't given you the design yet. Okay? I mean, we have found this ultimate gain, KCU, and the ultimate period, PU. We have measured those, but we haven't designed the controller yet. These are parameters that I measured from the sustained oscillations with the plant. Okay?
Ya ben şey demiştim de hocam, hani eğer j omega aksisinde olursa sustained ise hani bu ikinci elde ettiğimiz gibi bir şey elde edemeyiz. Onun için farklı bir, daha küçük bir KC gerek.
Aynen öyle, zaten söylediğimi dinlemeden şey yaptınız. Zaten şunu söylüyorum size. Ben KCU'yu ve PU'yu ölçtüğümde bu aşağıdaki gibi %25 decay ratio elde etmiyorum. the design parameters that would give us the 25 decay ratio are to be given right now here. Let me finish and then you ask your question again, okay? So as you said, for the proportional coefficient, I will have KCU over 2, right? That's your answer, right? For a proportional controller, no parameters for tau I and tau D, okay? So it's not KCU that I'm using directly. I'm using actually half that gain in order to obtain 25 decay ratio, okay? Sorunuzu cevaplıyor mu bu?
Evet hocam.
Tamam. So if you want a PI controller, then you go even further. So you divide KCU by 2.2, and also you have PU over 1.2 for the time constant, integral time constant, and you have KCU over 1.7 for a PID controller, PU over 2, and PU over 8. Okay, remember PU is a period, so you define the time constants in terms of the period, the ultimate period. Okay, obviously there are other variants. Okay, there are other variants computed for different decay ratios. Okay, so it's like a collection of let's say a long history of experimentation, and it gives you a practical test that you can apply with a system. Okay, now what is good about this method is that it doesn't need any model, okay, of the plant. It just needs to be kind of dominant second order behavior, and it needs to be going towards the unstable side as you increase the gain. Okay, so you find from which side of the gain you can approach instability, and you find the boundary of instability, and then you back off a certain amount in order to obtain a reasonably underdamped controller response. Okay, this method is in practice very useful. For example, in your senior year projects, if you end up using any controller, it's often very difficult to obtain an accurate model of the system that you are trying to control. So it really is quite difficult to develop a model from first principles and then find all the parameters and try to use our 302, EE302 types of methods to obtain a controller. But the Ziegler-Nichols method actually gives you a practical means of developing such a controller. Okay, so it's very easy to apply, but it also has some disadvantages as well. Now, do you guys have any questions at this point? Remember that this is a method that was developed in the 1940s. Okay? So, one of the problems is that it really pushes the control system to the limits, right? Pushes the controlled plant or process to the stability limits. Okay, I mean, there are certain obviously dangers with that, depending on what kind of system you have. I mean, think about having a nuclear reactor, right? You wouldn't want to use Ziegler-Nichols method to tune the controller for a nuclear reactor, I guess. Okay, because you wouldn't want to really wander around the stability boundary of that kind of a process. Okay, so so this is usually quite undesirable for naturally unstable plants. It may be difficult to come back from instability. Okay, I mean, theoretically, this unstable system may be very slow. If you're just on the very near, but on the right hand side of the j omega axis, hypothetically, you will have a very small exponential function. But in practice, once a system is unstable, you may not be fast enough to bring back the system to stability. Okay, so this may be difficult to turn back to stable behavior. Turn back to stable behavior. And as a result of that, you may end up even with sustained oscillations, because the magnitude of the oscillations can be quite large. You can actually damage something. Okay, you can have damage to equipment, and or you may have safety issues. Okay, so this is really a trial and error method, right? So that's an advantage. It does not give you too much of a theoretical basis. Okay, especially with very slow plants, this may be very time consuming. You may not even nor observe that the system is unstable, for example, so that you take an action. Or even if the system is not stable, the oscillations may be so slow that you may spend quite a bit of time. Okay, so this may be time consuming, especially when the process is very sluggish, is very sluggish. That means time constant is very large. For example, a large furnace, like an oven or a furnace that you're heating, may actually have a very very large time constant. So you may need to wait for quite a bit to observe the oscillations. Also, dr equals 1/4 may be unacceptable. For example, you may need much lower values, may need much lower decay ratio, or to eliminate oscillations completely. That is why I said there are many variants, right? There are such variants. Okay? Now, what you get from Ziegler-Nichols should really be considered as a starting point. You can always fine-tune, or play around with those parameters in order to get a better performance. Okay? These parameters often represent a reasonable starting point for, we may say, for a secondary tuning, manual tuning to get the desired performance. And what is the main advantage? I stated this already. The main advantage is that it does not need a system model, okay, and is experimental and feasible manually. Okay. Any questions so far? So I'm gonna basically give you an example. I will solve this example offline, okay? But let me give you the example itself to be solved offline. But I still want you guys to give it a try, okay? So this is PID with Ziegler-Nichols. But we will know the system model, and it's going to be a linear model, so that in fact we also have exact theoretical tools to kind of follow up what's happening with the Ziegler-Nichols, okay, or understand what's happening with the Ziegler-Nichols, okay. But on a given linear model, okay. So, and I will give you this in terms of physical system components. So we will have an actuator model, okay. Let's call this GA, and that's going to be given as 5/2s plus 1. So let's say the time constants are, let's say in this case TA is 2, and we should have some time unit here, and everything really revolves around the same time unit. You cannot give one time constant in seconds and another time constant in minutes, okay? If one of the time constants is in seconds, all of them should be in seconds, okay? Time constant with chosen units. In fact, in my notes, this is not seconds, but it is minutes. So this is more like a heating system or something like that, okay? Let's also define a sensor model. Let's call this GS of S, and that is equal to 0.4 over 5S plus 1. So if this is 2 minutes, the other one is 5 minutes, okay? Also a process model, okay? So GP of S is equal to 2 over S plus 1. So let me give you the closed loop system. So our closed loop system is something like this, right? We have a reference signal, R of t. Then we have the controller, GC of S, yet unknown. And then this drives the actuator, GA of S. And the actuator drives the plant, G of S. The plant, GP of S, the process model. The output occurs, okay? So this is usually known as the actuator signal. This is the plant input. This is our error signal. So this is our process variable, YT, often known as process variable, or the controlled variable. Okay? And then the output is measured, but this is through our sensor model, GS of S. And that gives the comparator signal. Okay? So what is the task? So let's say this is like an homework. Okay? Find the ultimate gain, KCU, and ultimate period, PU. Okay? Can you guys tell me how you can do that for this kind of system without simulation? Actually, I want you guys to be able to find these analytically, because now this system is fully given to you, and it is also linear. So you can actually do everything that is achieved by Ziegler-Nichols theoretically. Okay? Any ideas how to do that? No ideas?
Hocam biz burada close'da mı bakıyoruz, open'a mı bakıyoruz? Şeyde, genel olarak. Close'da bakmamız gerekiyor.
Sorunuzun cevabını bence siz verebilirsiniz diye düşünüyorum. Neye bakıyoruz? Close'da bakıyoruz, değil mi? Çünkü zaten başından beri closed loop testing dedik buna. Sistemimizi Ziegler-Nichols'ta kapalı döngü test ediyoruz. Çünkü bir proportional gain ile sistemi osilasyona sokmak demek, closed loop pole'ları o gain'i kullanarak hareket ettirmek demek. Öyle değil mi? Sorumu tekrarlıyorum. Ultimate gain'i nasıl bulacağız?
Belki o sensörü de şeyin içine katarak Unity feedback'e çevirip root 9 yaparak.
Unity feedback'e çevirmenize gerek var mı? Yani sonuçta root locus metodunda biliyorsunuz open loop transfer function kullanılıyordu. Open loop transfer function'da burada open loop'taki bütün component'ların Laplace domain'de çarpımı anlamına geliyor, değil mi? Yani GC of S, GA of S, GP of S, GS of S. Değil mi?
Ama sensör etkisinde katmamız gerekmiyor. Onun için closed loop'u da değiştirmez mi? Sensörün transfer function farklı olur.
Sensörün etkisini katmazsanız o zaman sistemin kapalı döngü davranışını modelleyemezsiniz. Çünkü kapalı döngüde sistem, yani open loop dediğim zaman ben aslında şunu söylüyorum. Karakteristik equation'ı ne olmuş oluyor bu sistemin? 1 artı GC of S, değil mi? GC of S'e siz ne diyorsunuz? KC diyorsunuz. Ne demiştik? İntegrali ve derivatifi kapatmalıyız dedik. Sadece proportional gain kalacak dedik. O zaman aslında bir tane root locus var elimizde. Yani 1 plus KC times GA of S, GP of S, GS of S. Right? Equals to 0. Bunun pollarını arıyoruz. Doğru değil mi?
Doğru da işte.
Evet. Değil mi? Yani 302'den hatırlayın. Sonuçta ben feedback loop'ta da bir şey versem siz bunun root locus'unu çizebilirsiniz. Çünkü tek ihtiyacınız olan characteristic equation'ın 1 artı gain çarpı bir şey olarak yazılmış hali değil mi? Hatta şey yapmıştık, herhangi bir arbitrary denominator'ın da root locus'unu çizebiliyorduk, öyle değil mi? Aynı şekilde. Yani herhangi bir karakteristik equation'ı, çünkü onu 1 artı gain çarpı bir rational fonksiyon haline getiriyorduk ve arkasından root locus'unu çizebiliyorduk, doğru mu? Dolayısıyla bu bir root locus problemi. How do you find a gain and period for sustained oscillations?
Hocam son dediklerinizi bir tekrarlayabilir misiniz?
Pardon. So if you have the root locus at hand, okay, or even you don't need to actually draw the full root locus, but assuming you have a root locus, how do you find the frequency of sustained oscillations or the gain value for which the sustained oscillations occur?
J omega veririz.
J omega ekseninin kesimini bulacaksınız arkadaşlar, root locus'un bundan ibaret, doğru mu? So that's what you need to do. Okay? So sketch the root locus. Even if you don't sketch it, just use the part that gives you the j omega axis crossing. What was the means to do that? Either you put j omega in place of s and you find the solution for the gain and the frequency, or you use, for example, Rod-Horowitz method to do the same. Okay? All right. So that concludes our Ziegler-Nichols method. Okay? And now I want to move on to design by open loop testing. Open loop testing. And that is also known as process reaction curve method. Okay? Process reaction curve method. Okay? So sometimes also known as Arkadaşlar, beni duyabiliyor musunuz? Arkadaşlar, beni duyabiliyor musunuz?
Evet hocam. Bugün biraz fazla kesildi.
Ee,
Bağlantı sıkıntı oldu galiba.
Şu anda nasıl?
Şu anda güzel hocam.
Tamam. So this design by open loop testing is, as I said, is based on a step response of the plant. That's why it's also called process reaction curve method. Reaction curve is the step response of the plant. Okay? Sometimes also known as receipt-based approach is also a strange name, but approach is some kind of an industry name for it. That is because previously derived tables are used for the design. Okay? So what's the procedure? You basically manually achieve steady state. That means you put the system in the operating point. So you do this around the operating point clearly in case the system is nonlinear. So you derive the model in the neighborhood of the operating point. Okay. So what you do is you apply bias, which is the steady state value, plus step input to plant. You collect the response data. Obviously, at this point, if you really are going to go with a linear model, well, you can do many options. You have many options. Okay, but if you have a nonlinear model, and we will specify this model, okay, fit a simple nonlinear model, and this is going to be our first order plus dead time nonlinear model. So that means obtain the model parameters, and use parameterized. Sesimi duyabiliyor musunuz arkadaşlar?
Geliyor hocam.
Parameterized design formulas to obtain the PID controller. Obviously, all subset of the controllers, right? PI, PID controllers can be obtained like this. Okay? But note, the model should be wire out to wire in. That means you should apply the step input just at the point of the output of the controller, so that all the effects of the actuator, the plant, the measurement system, everything is observed in the response. Okay, so you record the response at the point where the controller sees it. Okay, so that is called wire out to wire in. Okay, and these design formulas, we will derive some of these. Okay, so don't worry about it. So now let's come to this model that we want to fit to the plant behavior. Okay, so let's call this FOPDT, or first order plus dead time dynamic model. Okay. Now, what is the difference of this model from any, for example, first order or second order models that we have derived? In fact, there is also second order plus dead time as well. Okay. So what is this? This is a linear model, a transfer function basically, for example, first order, supplemented by the model of pure time delay. Okay. system should be overdamped for the model to fit, to be a good fit. Okay? So let me give you, so this is our process, right? We have the inputs. G of S is our plant or process, and we have the output. Now, this model that we are talking about, FOPDT, basically says that we have the system model as tau p dy of t over dt as a differential equation model plus y of t is equal to kp times the input but a delayed version, t minus theta p. Okay, so this is the time delay. Okay, so we assume that the input is somehow experiences a pure time delay, and then it goes into a first order differential equation. Okay, now you might think this is kind of something difficult to find, but in reality it's everywhere. There are many very common systems that have pure time delay. For example, if you have any communication in between the controller and the plant, such as a wireless network or a computer network or a lengthy cable, something like that, the signals would take some time to reach the destination. Your controller generates an action. You send that action to somewhere in a remote location through a communication delay, and then it's applied to the actuator. For example, in a car, there is a small computer network where microprocessors are sending signals, and they are communicated between microcontrollers to be applied elsewhere in the car. Same with a plane. Okay, so a communication delay is a typical example where you have a pure time delay. Also, there is something called a transport delay. If material is being transported from one location to another, you have delay. Let's say you have a fan. The fan pushes air, heated air, so the air travels a certain distance and heats a certain volume. In that case, you end up with a time delay. So this is a very popular way of treating those kinds of systems. So let me take the Laplace transform of this. Okay, so what I have is that I have, again, with zero initial conditions assumption, tau ps plus 1 times y of s is equal to kp. What is the Laplace transform of a time delayed signal? Do you guys remember? From Laplace transform properties, what is the Laplace transform of pure time delay? I can hardly hear you. Yes, that's correct, right? You have e to the power minus theta ps. So it's an S domain expression, but it's no longer a polynomial anymore. Okay, it's an exponential function of s times u of s. Okay, so what do we have? We have, in that case, g of s given by the ratio of the output to the input in the Laplace domain, and that gives us kp for the process time constant, process gain, e to the minus theta ps over a first order denominator, tau p s plus 1. Okay, so that is essentially. So what is the difference from a regular transfer function is that we have an exponential term here. Okay, which is the correspondence of a pure time delay. Okay.